About log function. We said something about log functions that we should always remember. That log functions are not they're not friendly. Why? Why am I saying that? When I talk about a function not being friendly, I mean it has restrictions. I have to worry about the fact that I cannot simply plug in anything I want. So
its domain is not real.
right, exactly. The square root is a problem, 1 over x is a problem, and now log is a problem. These three functions have restrictions. They are not friendly. I cannot simply plug in anything I want. So I have to worry about domain. So that's the situation with, if you remember when we square both sides to solve a radical equation, what is part of the problem also, of the solution?
Absolutely.
You have to go back and check, right? You have to go back and check. The same problem we have here with log. We have two options for log equations. We either state the domain, and the second option is we check back in the original problem. So this is a must. Do I tell you or force you to use one or the other? No. But you have to use one or the other at all times. Now, first possibility is check solutions. Of course, back in the original problem, in the original equation. This is one possibility. And the other one, state domain. I'm lazy when it comes to checking. I prefer the domain, but it's up to you. But you have to use one or the other. You choose which one, no one will indicate which one, but you have to do either check solutions back in the original problem or state domain. Okay, so let's start with our first problem. Let's say 54 on page 515. And that's log base 5 of x minus 7 equals 2. The reason I say, quote unquote, that I'm lazy when it comes to checking solutions is, first of all, I may forget. It's very possible. And the solution that I come up with may not work. So that's incorrect if I consider it the solution, but actually it's not. So first I have to write for this function, for the log function, I would like to determine its domain. And it's also a good practice for us because the domain is very important. So how do I write, what do I have to write in order to find the domain of this function? I have to write something to find the domain. What do I have to write? Yes? Exactly. Thank you so much. So this is x greater than 7, so the domain is 7 to infinity. So let's suppose I solve the equation and I get x. Yes?
How do you know it's the sign greater than 7?
Okay. So when we determine the domain, of this function, the log function, we said log cannot be applied to 0 and it cannot be applied to negative numbers. So we wrote 7 minus x greater than 0, and then we solved the inequality and we got the domain. Then,
so is it always going to be greater than every time you have a number in parentheses in the log form?
so if you remember when we graphed the two functions, the exponential with a base greater than 1, and then the log. Log is defined on 0 to infinity. So that's why we called it a long time ago when we discussed the function, we said it's not friendly. We have to worry about it. The domain must be, depending on what expression we have, but log cannot be applied to 0 and it cannot be applied to negative numbers. it behaves sort of like the square root or the fourth root or the sixth root. But it's not the same function, but it has restrictions, and the restrictions are pretty similar. I can plug in 0 here. I can have 0. I can have x equals -1, because I can take the square from 0. But here we cannot have x being -6, because -6 plus 6 is 0, and log of 0 is a vertical asymptote. You cannot plug in 0 in log. So when we look at a graph of pure log function one more time, with a base greater than 1, see, this is a vertical asymptote. So the function is not defined on this side. Therefore, so this is, I graph natural log x. So therefore, the function log, natural log x, must have a domain of greater than 0. Even if we look at the other one with a base less than 1, the other one with a base less than 1 will look like this. Let's say log base 1/2 of x. Still x must be greater than 0, because there is nothing on this side. And it still has the same vertical asymptote, that is x equals 0. Better? Perfect. Please redo the problems we do in class. That's where you get the knowledge for the class. Please. This is what I would do. Very first step, as many times as I needed. Okay, so coming back, we have the domain. What if I solve the equation and I get the solution x equals 5? What will you say? I chose the method of stating the domain, so I have the domain. So what if I get x equals 5? Will I accept it or not? No, because it's not in the domain. What if I get x equals 15, for example? I will accept it because it's in the domain. That's all I need to do. Just check against the domain. I no longer need, once I state the domain, there is no need to go back and check and plug it in the original problem. Now, you can say, I don't like stating the domain. I accept that. That's fine. You don't want to say the domain? That's fine. Then you have to go back and check. If you don't and the solution doesn't work, then you will not get credit for it, right? Full credit. Okay, so please be very careful with this equation. Okay, so now I'm going to copy it here one more time. You don't have to copy it. So x minus 7 equals 2. I don't know how to solve the log equation, but I know the most important concept in this chapter is that any log equation can be replaced by the most important concept in this chapter. Any log equation can be replaced by, say it again, an exponential equation. Very good, awesome. Any log equation is equivalent to an exponential equation. But how do I write the exponential equation? Can anyone dictate how to write the exponential equation that is equivalent to this? In other words, if I solve this, or if I solve what you're going to give me on this side, it's the same thing. Anyone? We always start with a base, and we go counterclockwise. 5 raised to, not multiplied, 5 raised to, I'm not saying you said that, I'm just refreshing your memory. 5 raised to the second power equals x minus 7. Awesome. So then 25 equals x minus 7, so x equals 32. Would you accept 32?
Yes.
Yes, because it's in the domain, which is greater than 7. So I will not have to go back and plug it in. Good. So this was our very first log equation. Let's continue with, you feel free to choose. Let's continue with 72. And you can choose the next. Any questions from me? 72, log base 4 of x plus 2 minus log base 4 of x minus 1 equals, they say 72 equals 1. Check if I copied correctly. Sometimes I don't. My apologies. Okay, I think I copied correctly. Okay, so now, how many functions, how many log functions we see in this equation?
2.
Exactly. In order for this to exist, what condition will you tell me to write? Yes,
Negative 2.
I have to write it for everyone to see.
Oh, sorry. So I put x plus 2 is greater than 0.
Perfect. For the condition for this to exist.
X minus 1 is greater.
Very good. These are the only conditions I have to state in case you agree to find the domain. Then this one is greater than negative 2 and this one is greater than 1. I want the intersection of these two intervals because I want both functions to exist at the same time. So watch this for a second. So this is negative 2 and greater. And right here somewhere is 1 and greater. So I need to find the territory that fulfills both conditions at the same time. From negative 2 and greater, and from 1 and greater.
Wouldn't it have to be 1 to infinity?
Exactly. So the domain must be 1 to infinity. It has to be a common domain. We discussed the common domain when we talked about addition and subtraction of and multiplication and division of functions. This is a difference of two functions. I need the common domain. The first one says from negative 2 and higher. The second one says from 1 and higher. Now, let me graph this just to make sure that everything is clear. So this is negative 2 and higher, and this is 1 and higher. We're not going to do this for all of them because I'm sure you're going to understand this quickly. So obviously this is the common territory. That's why if the solution is not a number between 1 and infinity, you will be disregarded. Good. So now let's go back to the equation and tell me, how do we condense the left-hand side? We cannot change this log equation into an exponential one as is. Not possible. That's why we learned how to condense and expand. So this time I have to condense. Can anyone tell us what will replace this? Log base 4 of what? It's in your notes last time. But say it again. Excellent. Thank you, Lani. Indeed. Awesome. So it's a difference of two logs. It must come from log applied to a ratio. Excellent. Now I can change it into an exponential. A word of caution. You cannot condense the two logs and then write the domain. It's not going to work. You have to write the domain on the raw equation. Don't touch it. Write the domain, and then you can condense it. Do not try to write a domain after you condense it. You're not going to get the same thing. Careful. Yes?
Would it? Your domain was 1. Let's say x equals 1. But it can't be 1 because it's parentheses. Never mind.
That's okay. Good. So now we are ready to change this into an exponential equation. Please tell me how to change this into an exponential equation.
So would be 4 to the 1 power equals x plus 2 over x minus 1.
Excellent. Now this is coming from our past. What is it and how do I solve it?
The rational.
Exactly. What does that mean? What am I telling you to do? Very good. So I cross multiply. So I have 4x minus 4 equals x plus 2. Now this is linear. I subtract x and I add 4. So I get 3x equals 6 and x equals 2. With a question mark, I don't know. Yes. It is correct because it's in the domain of 1 to infinity. And I'll say yes. I don't have to go back and check because I made the effort to find the domain. Questions so far? Questions? Okay, let's look at 88. Please choose. Choose the next one. 88 on the same page. Log x plus 3 plus log x minus 2. And on the other side equals log 3. Yeah. Log 14, sorry.
So are the bases 1?
Very good question. That was my question.
Or is it 10?
The base is 10. Base 1 does not exist. Base 0 does not exist. And negative base does not exist. So the base is 10. Very good. I was going to say the same thing. I was going to ask, I don't see a base. What is the base? Excellent. Good. So what is the condition that I have to write for the first log to exist?
X plus 3 is greater than 0.
Excellent. What is the condition for the second log to exist?
X minus 2.
The last one is log of 14. It exists forever. That's just a number. So this one is greater than negative 3, and this one is greater than 2. Yes?
Do you know where the base is 10?
It's from the graphing calculator. We have also, it's right here, log. So that's log is base 10, and the key with the second that it needs to be activated with a second, it's 10 to the x. So log and 10 to the x share the same key. So they have the same base. So by convention, base 10 is not written. Everything else is. Like with the square root, we don't write the index 2, but we write it for everything else. Good. So can anyone give us the common domain or the domain of these two? Right. It's very clear. Excellent. We don't have to graph it anymore. I knew that. So now please tell me, how do you condense the left-hand side?
Is it the whole thing? Will it be 1
I have to write log.
log and then I'm sorry.
That's okay. No worries.
Yes.
So it's the sum of two logs.
So you multiply x plus 3 and x minus 2.
Excellent. Indeed. So I condense the left-hand side. It's the sum of two logs. It must be log applied to a product. Very good. Well done. So now here's my next step. I do not need to change this. This is not a number. I mean, it is a number, but it's already log of 14. So here's my thought. I throw no thought. This side equals this side. And they have the same log and the same base. What has to happen to these two quantities for log of this to equal log of this? Can I have here 15 and here 14?
So the product, wait, is that log 14 then? Or is that log and then 14?
So the base is written here.
Okay, I just.
It's very, yeah, it has to be, I will erase it, but the base, so the log, if log is followed by something at the same level, it's not the base. But if it's very, very low, where the G ends or whatever, then that's the base.
So would we set the product equal to 14?
Exactly. X plus 3, x minus 2 equals indeed 14. In this particular situation, we did not need to change into an exponential equation. So what do I do next? Exactly. Very good. X squared minus 2x plus 3x minus 6 minus 14 equals 0. Of course. It's quadratic. I will have to get two solutions. I will have to FOIL and, of course, move 14 to the other side, combine like terms. We know this for like forever. So this is x squared plus x minus 20 equals 0. And you're going to give me the factored one. Excellent. Well done.
Oh, X, I'm thinking of the symbols real quick, but I know it's gonna be 4 and 5. It
Good.
would be plus 5 minus 4.
Excellent. So we have two options, and the options are
Or negative 5 and positive 4. And only positive 4 would fit.
absolutely, because we took the time and we stated the domain. Only this one fits, the other one doesn't. Very good. Well done. Any questions? Which one? 90?
Yeah.
Very good. Let's do it. Any questions on this before we look at 90? Any questions? Okay, so let's take a look. 90. Log base 2 of x minus 1 minus log base 2. You will not see two different bases in the same equation in this class. Log base 2. However, it's not difficult. We can always use the change of base formula, but you're not going to see that. Good. Perfect pick. The condition for the first one?
X minus 1 is greater than 0.
Excellent. For the second one? Excellent. And for the last one? Excellent. Great job. What does the first one say? X
Positive 1.
greater than 1. What does the second one say?
X is greater than negative 3.
Very good. Now let's think. The top is positive, and there is the denominator that could be anything, except 0, of course. The top is positive. The bottom I don't know, but I want the whole thing to be positive. What could the denominator be?
Negative.
But one positive of a negative is not going to be positive, right? So x must be positive. Otherwise, 1 over negative will not be greater than 0. Is that clear, everyone? Perfect. So now, greater than 0, greater than 1, greater than negative 3. What do I pick? Where? Say it again. Excellent. Well done, Jody. Thank you. So common domain 1 to infinity. From negative 3 to your right, from 0 to your right, and from 1 to your right. Of course, 1 takes care of everything. Good. So let's condense the left-hand side. The right-hand side can wait.
So we would put it over each other.
So what do I write?
Log 2
Log base 2.
x minus 1 over x plus 3.
Excellent. Don't cross out anything. Don't simplify anything. This is the thought right now. Two logs are equal, and they have the same base. Because if they don't have the same base, it's a different story. I have to do something about it. Two logs are equal, and they have the same base. What has to happen to the quantities we apply log base 2 to?
They have to equal.
There is no other way. So x minus 1 over x plus 3 must equal 1 over x. What do I do now? Indeed. That's why we studied this a long time ago. So we have x squared minus x equals x plus 3. Good. Look at how many steps we had to go through. Number 1, we had to find the domain. Number 2, see how much we can test with only one problem. Stating domain, finding common domain of functions. Number 2, condensing. Number 3, thinking of the fact that the log function is 1 to 1 and two logs are equal, then the expressions have to be equal. Then we have to identify that this is a rational function called proportion. Then we cross multiply. Now we have a quadratic function, and it goes on and on. A lot of steps. So this is not a trivial problem at all. So then x squared minus 2x minus 3 equals 0, and then I'll try to factor.
X minus 1, x plus 3.
The other way around, x minus 3 and x plus. Isabel, you said x?
Negative 1 and positive. I had the symbols wrong.
That's okay. My apologies if I heard something else.
No, that makes sense because the 2 would have to be negative.
So then, now we have to make a decision. And that's why we stated the common domain. So I don't have to go back and check. Indeed, I'll say yes, and I'll say no. Very good pick, Priscilla. It was an interesting problem. Okay, so let's move on, and then we'll come back. We're going to have more equations right here, right now in word problems. Okay, last section of chapter 4, 4.5, applications. Of course, applications with exponential and log. There are three major applications here. There is so much really, but three main applications. Exponential growth. And I was mentioning some time ago, bacteria, rats, fish, rabbits, bats grow exponentially. Populations grow exponentially. The second is the exponential decay. The exponential decay refers to radioactive substances. They diminish their mass in time. There are other models too, but this is an exponential decay referring to a radioactive substance. If you remember, we looked at a problem at the beginning of chapter 4 in which the explosion from Chernobyl nuclear plant, if you remember, and we said, when can these people go back to their homes? And it was some sort of radioactive substance still in the atmosphere. So it diminished its mass by now, but not sufficient to be safe for habitation. So they couldn't go back. So that's exponential decay. Okay. And the last one is logistic growth model. So these are three main problems, main categories of word problems or applications here. Of course, I should add what we already discussed in section 4.1. What was it? Interest compounded n times a year, and the continuous compound interest. So we could add those two to the list of three. Interest compounded whatever per year, and the continuous compound interest. So we can add those in here. So let's say two more. Compounded interest, n times per year, as we know. I'll put it in parentheses. And continuous compounded interest, which we discussed. Yes, Steve?
So are those parts of logistical growth modeling?
No,
Okay.
these are two other options.
Okay, gotcha. Thank you.
Sorry about that. So we have 5 different situations. Exponential growth is one. Exponential decay is the second one. Logistic growth model is the third one. Interest compounded n times a year, and continuous compound interest, that's a 5th one. We already looked at problems with these two, so that's why I just wanted to refresh our memory that we looked at those before. So let's take a look at the exponential growth. You do not have to memorize any of these models. They will be given to you. Okay, so exponential growth. Exponential growth. A of t equals A0 e to kt. Again, you don't have to memorize it. I'm just telling you what it means. It's very, very similar to continuous compound interest. Very similar. This is the initial number. Bacteria grow exponentially. Populations grow exponentially. It could be the initial number of bacteria. K is the growth rate. T is time. And A of t is the amount. So initial number, or the number at time t. And let's apply this model in an application. on page 530. 529, 530. Are we interested in looking at Israel's population or the Palestinian population? Problem 7 or 8? Or I'm looking at the end of the chapter. If we're not interested in either, we can look at problem 86 on page 538. I don't see any other exponential growth models here. Okay, you're not excited about either one, so let's do 86. So 86 on page 538. According to the U.S. Bureau of Census, in 2000 there were 35.3 million residents of Hispanic origin living in the United States. By 2010, the number had increased to 50.5. Okay, the exponential growth function is given to us, a of t as 35.3, of course, the initial, times e to kt, where this is the growth rate not given. Describes the U.S. Hispanic population A in millions, t years after 2000. So t is in years. And t equals 0 means 2000. How do I know? One more time, let's read this. The exponential growth function, blah, 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 describes the U.S. Hispanic population, A, in millions, t years after 2000, which means the initial t equals 2000. T equals 0 means 2000. Part A, find k correct to 3 decimal places. So part A, find k. Okay, so let's summarize what we have. We are told that in the year 2000, meaning when t is 0, the population was 35.3. When t is
10.
Very good, the population is 50.5. So obviously, can anyone give us a point, an ordered pair for this? 0, comma, 35.3. Very good, I know. So now for this one, can anyone give us a point? Yes, comma, 50.5. Very good. This was already put in the calculation. How do I know? Bless you. So when t is 0, let's put it in for everyone to see. So the function is a of t, 35.3 e to kt. So a of 0 is 35.3. This is what it means, correct? A of 0 equals 35.3. So when we plug in 0, in the left-hand side, we get 35.3. This is 35.3 times e to k times 0. But how much is k times 0? How much is e to 0? Very good. So the first point was already put in the equation for us. But the second one is not, or wasn't. Can anyone give us an equation for the second point? In the same way we wrote the first equation for the first point.
So A of 10.
Very good. Equals
35.
50.5. Perfect. So now, tell me how to write this based on what we have. Like we wrote here, a of 0. This left-hand side is 35.5. Now it's 50.5 equals 35.3 times e to k times Excellent. Or 10K. Great job. So we put in this in the equation the second point, which is 10 comma 50.5. Great job. Now I have to solve this equation for what? For K. Remember, we always clean up equations before we do anything. What would be the cleaning up step that I have to perform?
Get K on one side of the equation.
I can't just yet. It's multiplied by something.
Minus 35.
I cannot subtract because it's multiplied.
Divided by.
Excellent. 50.5 divided by 35.3 equals e to 10K. From last time we said this. Every time we cannot present both sides with the same base, we have no choice but to do what? Apply to both sides the inverse function. What is the inverse function of the exponential?
It's radical.
Has nothing to do with the radical. That's why this chapter presents exponential and log, not radical and exponential.
We could take the log.
I have to apply log. I have to apply log to both sides. Remember, exponential and log are together because they are inverses of each other. Perfect. The left-hand side is natural log of 50 divided by 5. Do not calculate anything. But now, let's see what we have on the right-hand side. Can anyone help with the right-hand side? Property number 3 of logs.
Do you move?
Exactly. What?
Do you move both the 10 and the K to in front, or just the 10?
They are multiplied.
Okay.
I have to move the entire power. I cannot break the power. Very good question. Yes, 10K goes in front, but now we discussed this last time. How much is natural log E? Excellent. Thank you, Mama. Natural log E is 1. You can write it, but there is no point. It's 1. Therefore, I have K. What do I do to get K?
Divide 10.
Excellent. Well done. Natural log 50.5 over 35.3. I'm not going to do any of this by hand, of course. I will go directly to the calculator and put natural log 50.5 divided by 35.3, close the parenthesis, and divide. Since there is only one factor in the denominator, I'm okay. It says 4 decimal places. So I'm going to write 0.0358. This is the growth rate. 0.0358. You can write 3.58%. But we cannot use it. We cannot use percent anywhere. But I do have the entire model now. Now we are happy. It's A of t 35.3 times e to 0.0358 t. There are no more secrets in the model. We have, oh, and now we can answer the next question. Use the resulting model to project the Hispanic resident population in 2015.
So 15 would be T.
Exactly, because t equals 0 is 2,000. So A of 15. Let's plug it in. So we had 35.3 times E. In parentheses, please. I'm going to recall the previous answer because I don't want to truncate it if I can. Avoid it. Times 15. I'm going to get a better approximation than if you truncate. So here it is. 60.4 million. Part C. In which year will the Hispanic resident population reach 70 million? So my apologies, this was part B, and now part C. In which year will the population reach 70 million?
Would you have to put 70 million in per se?
Of course, because that's the amount, that's the number. Excellent, well done. 70 equals 35.3 e to 0.0358 t. And now there is a lot of repetition, as you see in this chapter. What do I do next? I have to clean it up, as we did a minute ago.
Would be
Exactly.
divide 35.3.
Yes. And now, I look at the left-hand side, I look at the right-hand side. It's an exponential equation. I wish I could present both sides with the same base, but there is no way. But I do have a mechanism. And the mechanism is what? Very good. We apply natural log to both sides. So then natural log 70, say it again.
We have to bring the
0.0358 t. I should write times natural log e, but how much is perfect? So then t equals natural log 70 over 35.3.0358. Now I have no choice. I can no longer recall the previous answer because I already have the previous answer is 60 million, so I can't do that. So I have no choice. Natural log, parentheses, 70 divided by 35.3, and close the parenthesis, and now I have no choice. I have to divide by 0.0358, and enter. What does this mean?
In a little over 19 years.
Excellent.
This would help it.
So so it appears that this should be roughly 19. So this year, assuming the model still holds, the population will reach 70 million. Any questions?